Lighthouse Scientific Education presents a lecture in the Measurement and Numbers series. The topic of the lecture, Math for Chemistry, Part 1. Math for Chemistry. We will begin by reviewing the fundamental properties of mathematics. Then take these properties and outline the basic steps of algebra that are used in solving for a variable. From there, fractions and fraction math. There will be other fundamental mathematical processes covered in other lectures. This includes solving for a variable in a multiple variable equation. This will be done in lecture Math for Chemistry Part 2. Percent, that will also be covered in Math for Chemistry Part 2. Exponents, specifically exponents of the base 10, will be covered in the Scientific Notation lecture. Rounding off of numbers is covered in Significant Figures. There are also other fundamental mathematical processes that we will not get to because they are infrequently used at this level of chemistry, and they include logs and roots. We will treat mathematics like we're going to treat chemistry. That is, we will build up from the fundamental properties or fundamental laws. The most straightforward of these properties is the commutative property. The commutative property of addition. It says a plus b equals b plus a. An example of this would be 6 plus 8 equals 8 plus 6. And we see that if we do the addition on both sides of the equation, we get 14 equals 14. The commutative property of multiplication says a times b equals b times a. Example of this property is 6 times 7 equals 7 times 6. Multiplying each side out gives 42 equals 42. The commutative property, it may not seem that it's that important. It may seem a bit obvious, but these are mathematical laws that allow us to rearrange the order of terms in addition equations and in multiplication equations. The next property is the distributive property. It says that a times b plus c is equal to parentheses a times b plus parentheses a times c. That multiplication sign is a dot here in front of the parentheses. It's not needed, but it's included to demonstrate that the a is multiplied by the b and the a is also multiplied by the c. And these are done separately. And while we're at it, there are several other ways of writing the multiplication sign, including this dot, the familiar x, or by just putting two variables next to each other. A demonstration of this law is 6 times parentheses 7 plus 8, which is equal to parentheses 6 times 7 plus parentheses 6 times 8. Doing the math in the parentheses gives us 6 times 15 equals 42 plus 48. Finishing the math, we have 6 times 15 equals 90 and 42 plus 48 also equaling 90. The next property is the associative property. It's concerned with grouping of terms. The associative property of addition says a plus b, or parentheses a plus b, plus c equals a plus parentheses b plus c. Demonstration of this law is parentheses 7 plus 8 plus 6 equals 7 plus parentheses 8 plus 6. Doing the math in the parentheses first gives us 15 plus 6 equals 7 plus 14. And finishing the addition, we see that each side is equal to 21. Similarly, the associative property of multiplication shows that different terms in multiplication problems can also be grouped together. The law states that parentheses a times b times c equals a times parentheses b times c. Our example, parentheses 2 times 3 times 4 equals 2 times parentheses 3 times 4. Doing the parentheses math first gives us 6 times 4 equals 2 times 12 are equal to 24. So problems with just addition or just multiplication, the way numbers are grouped, does not change the final value. The last property we want to talk about, and the most important for algebra, is the identity law. There is an addition identity law and a multiplication identity law, and both laws are used repeatedly in algebra. We will look at the identity law of addition first. It states that a plus 0 equals a. That works for 5 plus 0, which equals 5, and x plus 0, which equals x. The companion law is for subtraction. It states that a minus 0 equals a. That works for 5 minus 0 and x minus 0. Now, this may again seem overly simple, but if we expand on the notion of 0, it can become quite a powerful rule. First, we will consider positive values. A positive value can be made equal to 0 by subtracting the value from itself. For example, to make a positive 5 equal to 0, subtract 5. This is really just a rearrangement of the identity law equation. And to make a positive x equal to 0, again, subtract x. If we're starting with a negative value, these can be made into 0 by adding the positive of that value. So if we start out with a negative 5, we can add a positive 5, and it comes out to 0. Again, the same thing, a negative x, add a positive x. Let's do some algebra by putting the identity law of addition together with this concept of making a term, be it a variable or a number, equal to 0. Consider the problem x minus 5 equals 8. It is an algebraic expression that is solved by isolating x on one side of the equation and numerical values on the other. It's not so difficult a problem that we can't probably guess the answer, but we will use these laws and relationships we've covered to solve it. So to isolate x, we can begin by getting rid of or removing that negative 5. But we can't just erase it. What we can do is make that negative 5 equal to 0. And use the identity law that will isolate x for us. But how do we make a negative 5 equal to 0? We add a positive 5 to it. And if we add a positive 5 to one side of the equation, we add a positive 5 to the other side of the equation. Using the associative property of addition, we can put parentheses around the 5 minus 5 and show that it's equal to 0. This is not a necessary step, but it helps demonstrate the current concept of interest. So let's go ahead and do the parenthesis math, and we will have x plus 0 on the left-hand side of the equation. And this is equal to x. So we've isolated x on one side of the equation. We need only to finish the math on the other, and that will get us x equals 13. Let's try another. 4x equals 8 plus 3x. Again, we want to isolate x on one side of the equation and have numerical values on the other. We see that we have variable x on both sides of the equation, so we're going to need to move one of those x terms to the other side. It doesn't matter which side. We'll go ahead and move the 3x. To do that, we need to make the 3x equal to 0, so that we can have 8 plus 0, and use the identity law. And we can do that by subtracting 3x from both sides. Applying the associative property of addition, we can put parentheses around 3x minus 3x, which we know equals 0, and 8 plus 0, which equals 8. Now all we have left to do is the subtraction of the x's, where 4x minus 3x equals x, and we have our answer, x equals 8. When dealing with addition, or an and subtraction, and algebraic expressions, you can use the identity law of addition and the ability to turn any value into 0 to move values from one side of the equation to the other. the other identity law. That is the identity law of multiplication, and it states that a times 1 equals a. Any value multiplied by 1 returns that value. That's identity. So 5 times 1 equals 5, and x times 1 equals x. The number 1 can also be used in the identity property of division. A divided by 1 equals a. 5 divided by 1 equals 5. X divided by 1 equals x. With the identity law of addition, we expanded on the notion of 0. Here, we're going to expand on the notion of 1. Anything divided by itself is equal to 1. 1 is an extremely powerful number and will be used frequently in problem solving and unit conversion. 1 can take many forms. 5 divided by 5 is 1. X divided by x equals 1. 1 foot divided by 1 foot equals 1. Anything divided by itself equals 1. 1 foot divided by 12 inches also equals 1. The same argument can be made if we flipped it around and we put 12 inches on top and the 1 foot beneath it, because 1 foot is equal to 12 inches. We can combine the identity law of multiplication with the divided by itself to create one process, and we can begin to see the roots of algebra. 8 times 1 in the form of 5 over 5 is 8, returns itself. X times 1 foot over 1 foot also equals x. And x times 1 foot over 12 inches, where we know that 1 foot is equal to 12 inches, is going to be also equal to x. That last one is going to be an example of a conversion factor. In each case, a value was multiplied by a version of 1, and it returned the value. With this combined expanded law of multiplication and version of 1, we're ready to take on a multiplication algebra problem. Our first demonstration uses 5x equals 15. Again, a problem that can probably be solved by observation, but it serves our purpose. If by solving we mean getting x by itself, then we need to do something about that 5 in front of the x. This is where the identity law comes into place. If we can turn that 5 into a 1, then 1 times x, or x times 1, will equal x, and the variable is isolated. Note that we cannot subtract the 5 out. Subtracting out of multiplication, that math just doesn't work. But if we divide both sides of the equation by 5, we get 5 over 5, which we know is equal to 1. And 1 times x equals x. All there's left to do is divide 15 by 5, and we get x equals 3. We move the 5 to the other side of the equation, though now it's in the denominator, with division and the identity law. A more complex problem is a hint at things to come. It is a conversion problem, and it uses the exact same set of steps as the algebra problem. We see here that it is already solved. 3 feet equals 36 inches. The objective is to show how this is accomplished mathematically. We will use the identity law and multiply 3 feet by 1, but not any old one. We need a 1 where the units of feet cancel out. That means they need to be in the denominator. Watch. Previously, we've shown that 12 inches divided by 1 foot is equal to 1. This concept is explored in more detail in dimensional analysis lecture. As written, the unit factors of feet cancel out, leaving just the units of inches. And 3 times 12 inches equals 36 inches. We will see this step many times in the lectures to come. The addition and multiplication identity law along with the process for generating zeros and ones, combine to form the basis for general algebra. Consider the following problem. 5x plus 7 equals 2x minus 2. The first step in solving this problem is to collect like terms. Bring all the x's over to one side of the equation and all the numbers over to the other side. It doesn't really matter which side we choose to collect the x's on. The problem is solved when one side of the equation has x by itself and the other side has a numerical value. Here's a tip. It's far easier to use the addition identity law before the multiplication law. To restate that, go after the pluses and minuses before the multiplications and divisions. As such, the multiplication identity law should be used as the last step. Our first maneuver will be to turn 5x plus 7 into 5x plus 0. This is done by subtracting 7 from both sides of the equation. The associative property allows us to group the 7's, and solving the math inside the parentheses gives us a 0. On the other side of the equation, minus 2 minus 7 equals minus 9, and 5x plus 0 equals 5x. Now we need to move the 2x over to the left-hand side of the equation. This is done by subtracting 2x from both sides of the equation. Grouping shows us that subtracting 2x from the right-hand side of the equation will give us a 0. And 0 minus 9 is minus 9. The left-hand side of the equation simplifies to 3x. So now we have 3x equals minus 9, and we are ready for the multiplication identity law. We need to turn the 3 in the 3x into a 1. Subtraction is not an option because 3 times x is really x plus x plus x. There is no 3 to subtract. We can instead divide both sides of the equation by 3. 3 divided by 3 is equal to 1, and 1 times x is equal to x. Negative 9 divided by 3 is equal to negative 3. And we have our equation x equals negative 3. We have our solution. To review the process, we start by collecting like terms, moving all the variables to one side and all the numbers to the other. We turn terms that are added or subtracted into zeros so that we can use the addition identity law. This effectively moves the term to the other side of the equation. It does, however, change the sign. Then, if there is a number in front of x that is not 1, we can convert that number into 1 by dividing by its own value and using the multiplication identity law. Remember to watch your signs and to write the problem out with each step clearly shown. That generally requires you to write the equation multiple times, which may seem like it's more work, but in the end it cuts down on errors and it prepares you to become a better problem solver. Our last major topic is fractions. A fraction is a ratio of numbers. The bottom number is called the denominator, and that gives the size of portions or how many parts. The top value is called the numerator, and that gives the number of portions or parts. While we're at the definition stage, there's a help property of the division part of the identity law that makes it easier to do math with whole numbers and fractions. Any number can be made into a fraction by dividing it by 1. If we start out with a straightforward equality, like 8 equals 8, and we divide one of the 8's by a 1, we still have that same equality, but now we have a fraction. So by default, the denominator of a whole number is 1. It's helpful to consider the fraction as a division problem. Say we have the fraction 3/4. What we're really saying is 3 divided by 4, and that's 0.75 in decimal form. Verify that this is what you get when you divide these numbers into your calculator. If we have the fraction 4/3, it says 4 divided by 3. And that yields 1.33 ... where the dot means the 3's go on forever. As for fraction math, adding and subtracting fractions require that the fractions have the same denominator. The sum of 1/2 plus 1/3 is not immediately obvious. Answers like 1/5 or 2/5 or 1/6 are doing the math incorrectly. We can take a closer look at this using a couple hypothetical pies. Our first pie is cut into 2 pieces, which means that a fraction describing the pieces of the pie, such as the blue piece, will have a denominator of 2. Since only one piece is colored blue, and our fraction of interest is the pie, which is blue, the numerator will be 1. 1/2 of the pie is colored blue. The second pie is in 3 pieces, and the fraction describing it will have a denominator of 3. And again, only one piece is blue, so the numerator is 1. We can see that adding the blue pieces together will not quite give us a whole pie, but the exact proportion is not so clear. 1 piece plus 1 piece does not equal 2 because the pieces are a different size. But what if, for the first pie, we cut each half of the original pie into 3 pieces? There will now be 6 pieces or portions. The amount of blue is the same it was in the original cut, but if we count how many pieces there are blue, we have 3, which will be our new numerator. We can show this mathematically if we start with 1/2, and employing the identity law of multiplication, we multiply by 1, in the form of 3/3, since each slice of pie was cut into 3 pieces. And getting just a little bit ahead of ourselves, we multiply the numerator of the 2 fractions together, and then the denominator of their 2 fractions together, and we get 3/6. 3 pieces of blue out of 6 total pieces. Okay, we've made equal value equations with 1/2 and 3/6. The fraction has a different denominator, but it's still the same fraction. The second pie can also be cut into 6 pieces if we cut each piece in half, again starting with 1/3 and employing the identity law of multiplication, that is multiplying it by 1, in the form of 2/2, since each slice of pie was cut into 2 pieces. We will get 2 times 1 over 2 times 3, or 2/6. The value of 1/3 can be converted into 6 without altering its value. Now that our fractions have the same denominators, we can do the math on the numerators. 3 plus 2 equals 5. We have 5/6 blue. Looking at the pie, we see that the only way that the numerators can directly add is if they are the same proportion, 6. So adding and subtracting will require fractions that have the same denominator before doing math on the numerators. It's not always fun, but that is how it's done. Multiplication of fractions is much easier. When multiplying fractions together, multiply the numerators together, and then multiply the denominators together. When the fraction a/b is multiplied by the fraction c/d, the answer is numerators a times c over denominators b times d. 3/4 times 5/6 equals 3 times 5 over 4 times 6, which is 15/24. Usually fractions are reported in simplified form. 15/24 simplifies to 5/8, and that's done by removing a 5 from the top and the bottom. And that brings us to the first common practice used to make fraction multiplication easier and cleaner. Simplify before you multiply. Take the fraction 7/5 times 15/4 times 2/3. We can follow the rules for multiplying and multiply all the numerators together and then multiply all the denominators together, and that will give us the right answer. However, the new fraction will need to be simplified by removing common multiples from the top and the bottom. A better way is to remove common multiples before doing the multiplication when they're easier to see. The first common multiple to be removed here is a 7. There's a 7 in the numerator of the first fraction and a 7 in the denominator of the second fraction. It is within the 14. And if we remove the 7, there'll still be a 2, since 7 times 2 equals 14. Note that there is a 1 remaining from the 7 in the numerator of the first fraction. We can always write the number as itself times 1, as we saw in the identity law. So even if we cancel out the entire number, there will still be a 1 left over. Crossing out arrows and indicating what remains is a general practice of showing that a common multiple has been removed. There's also a 5 in the denominator of the first fraction and a 5 within the numerator of the second fraction that will cancel out. Note that a 3 remains from the 15. We can continue to cross out because there still are common multiples left, but let's take stock of where we are. If we multiply all the numerators together, 1 times 3 times 2, and if we multiply all the denominators, we have 1 times 2 times 3, and that's going to give us 6 over 6, which reduces to 1. There are many ways of doing this problem and coming up with 1. This way shows canceling out of common multiples before multiplying. The other common practice is called the removal of 1s. We actually did this in the previous example when we canceled out, but a demonstration of why canceling out is really removing 1s can be beneficial. We'll start with the same problem. But this time we'll write out the entire multiplication of the numerator and denominators, and we'll factor terms into their prime numbers when possible. We see that in the numerator, the 15 can be written as 3 times 5. Both are prime numbers. And the 14 in the denominator can be written as 2 times 7, also a couple of prime numbers. Next, we will rearrange the order of multiplication on the top and the bottom to align the same numbers. Why can we do this? The associative property of multiplication, one of our fundamental properties. We can also group terms that generate the value of 1. 7 over 7. 5 over 5. Again, there are still more possible groupings, but we'll continue to the next step. If we solve those parentheses, we end up with 7 over 7 is 1, 5 over 5 is 1, and what's left over is 3 times 2 over 2 times 3. And employing the identity law of multiplication, a value times 1 returns the value, and a bit of multiplication gives us 6 over 6 or 1. Therefore, canceling out and removing 1s are really the same thing. Choose the one that you like best, and remember, simplify before you multiply. Our final topic for fractions and for the lecture is division. The rule for division is flip the second fraction and multiply. The fraction a over b divided by c over d is equal to a over b times d over c. The d over c is the reciprocal, or the flip, of c over d. Now we can multiply, that is, multiply the numerators and then multiply the denominators, and we come up with a times b over b times c. An example, 3/4 divided by 6/7. What does the rule say? Flip the second fraction and multiply. The second fraction is 6/7. Flipping 6/7 gives us 7/6. Therefore, 3/4 divided by 6/7 is equal to 3/4 times 7/6. When the numerators are multiplied together, 3 times 7, and when the denominators are multiplied together, 4 times 6. Well, just because this question started out as a division problem doesn't mean that we shouldn't try canceling out before we multiply. The 3 in the numerator will cancel out with the 6 in the denominator, leaving a 2. Now we multiply the numerators together. 1 times 7 is 7, and 4 times 2 is 8. Well, that completes our coverage for Math for Chemistry Part 1. Let's recap what we've covered. We started at the foundation and covered some fundamental properties of mathematics. Of particular importance was the identity law of addition. Any value plus 0 returns that value, x plus 0 equals x. And the identity law of multiplication. Any value times 1 returns that value, x times 1 returns x. We use the fundamental properties to produce a process for solving for a variable. Isolating a variable requires moving terms or values across the equal sign. With addition and subtraction, values can be moved across the equal sign by making them equal to 0. With multiplication and division, moving the values done by making them equal to 1. Fraction math requires us to understand that fractions are division problems. When dealing with addition and subtraction, we need to get a common denominator before we do the math on the numerators. With multiplication, we just need to multiply across, numerators on top, denominators on the bottom. There are some standard practices with fraction multiplication. Simplify before you multiply, or remove ones, which we saw is the same thing as canceling out. And finally, with division, flip the second fraction and multiply. And that concludes the lecture on Math for Chemistry Part 1. Be sure to check out Part 2. Now, math and chemistry require practice. It's not enough to follow a lection. To build understanding requires effort and practice.